Alg3 Section 2, Polynomial Functions of a Higher Degree. Characteristics of graphs of polynomials. So graphs of polynomials are continuous. They have no sharp turns or corners. Functions of an even degree will have similar characteristics, and functions of an odd degree will have similar characteristics. And the simplest polynomial function or parent function is f of x equals x to the n, where n is an integer greater than 0. Okay, here we have an example of even graphs and odd graphs. We have x squared, x to the fourth, and x to the sixth all graphed on the same axis. And we have x to the third and x to the fifth. You can see the similarities between the even functions, and then you can see the similarities between the odd functions. Notice that the larger the power is, the flatter the graph tends to be as it gets close to the point 0, 0. Now, you need to note that at the left and right extremes of a graph, a polynomial will either rise, in other words, it'll go towards infinity, the y values will, or it will fall. In other words, the y values will go towards negative infinity. What happens is determined by the degree and the sign on the leading coefficient. Now we're going to look at end behavior, and we're going to start with odd functions. And here we have an odd function. Now, as we look at these functions, normally I tell you to read a graph from left to right, but when we're looking at end behavior, what I need you to do is kind of center yourself and think about the perspective from the middle of the graph. So look at 0, 0, and then we're going to examine what happens as the graph goes right from there and as it goes left. This particular function, and the odd functions, notice as you look to both directions, they'll go in opposite directions. So here, as you look to the left, the graph is going down, and as you look to the right, it's going up. Now, this particular graph will have a positive leading coefficient. And what that means is the very first number is going to be positive. What happens when you have a positive leading coefficient on an odd function is what we're seeing here. As x gets larger and larger and larger to the right, the graph goes up. But as x gets smaller and smaller and goes towards negative infinity on the left, y goes down. When you have a negative leading coefficient and you have an odd degree function, as x goes to the right, as it goes larger and larger towards positive infinity, you see that the graph will drop down and continue going down eventually. And as you go to the left with your x values, the y values go up, so it rises. So you can kind of get a feel for which shape it's going to have based on the fact that it has an odd degree and the sign on the leading coefficient. Now for even functions, as you start in the middle and look at the graph going in both directions to the right and left, both sides will either go up or they'll both go down. If they're both going up, then that means that your leading coefficient is positive. However, if they're both going down, as you see in this graph, then the leading coefficient is negative. And we've talked about this before in relationship to parabolas. So if you remember the characteristics of a parabola, you can kind of apply that to really any even degreed function. Some examples. Pause the recording, give this a try, and resume to check your answer. All right, on the first one, this degree is odd. It's x to the third. The leading coefficient is positive. So as x goes towards infinity, as x gets bigger and bigger to the right, it's going to go up, but to the left, it's going to go down. Our second one, even though it's mixed up, it is an even degreed function. The negative 3x squared should go first, and it begins with a negative, so this means that both ends, as x gets big and as x goes towards negative infinity, both sides are going to go down. Now to find zeros, you've got a couple of ways of doing this. You can set the function equal to 0 and solve, as we've done before, or you can graph it on your calculator and use the calc0 function. You'll hit second trace and then you'll 0. Given a polynomial function f of x of degree n, you will have at most n real zeros. In other words, the most number of zeros you will ever have in a polynomial is the same number as the degree. So a quadratic, which is x squared, can have no more than 2. A fourth degree equation can have no more than 4. 10th degree, no more than 10. The graph will have at most n minus 1 turning points, and these will be the maximum or minimum points. So take the degree and subtract 1, and that gives you the most number of turns you're going to see in the graph. Now, these statements all mean the same thing. X equals a is a 0 of f of x. Another way of saying that is x equals a is a solution of f of x equals 0. It would also be an x-intercept, and x minus a would be a factor. What they're trying to get you to see here is the relationship between x-intercepts, factors, and solutions or zeros. We're really talking about the same thing with all of these. Now, if we factor this particular equation, we get x plus 3 times x plus 3 equals 0. The solution to both of those factors is negative 3. Because negative 3 is the solution for more than one factor, it is called a repeated 0. In fact, when we write it as a power, x plus 3 squared, that power tells you how many times the number appears as a 0 of that particular function, and we call that the multiplicity of that 0. So negative 3 has a multiplicity of 2 in that equation. When a 0 has an odd multiplicity, then the graph will cross through the x-axis at that point. But when it has an even multiplicity, the graph will touch it, but it won't actually go through it to the other side. So what we're going to do is find the real zeros, determine the multiplicity, determine the maximum possible turning points, and graph to verify this. So graphing is going to be our final act. Pause the recording, give this a try, and resume to check your answer. Okay, we factor this into x plus 6 times x minus 6. That means our zeros are 6 and negative 6, each of them with a multiplicity of 1. Our highest power is 2, which means we have at most one turning point, and we can verify that with the graph. The next function factors into 3x times x squared minus 4x plus 1 equals 0. You really can't factor that next part. Instead, you would have to put it into the quadratic formula. So we have x equals 0 with a multiplicity of 1, x equals 2 plus the square root of 3 with a multiplicity of 1, and 2 minus the square root of 3 with a multiplicity of 1. It's a cubic equation, so the most number of turning points it can have is 2. Now try this problem. Pause the recording, give it a go, and resume to check your answer. Okay, factoring the first one, we get x times x squared minus 3 times x squared minus 3 equals 0. And you can solve that. If you set the x squared minus 3 equal to 0, you can solve it. And you get the square root of 3 and negative square root of 3. So we have 0 with a multiplicity of 1, square root of 3 with a multiplicity of 2, and negative square root of 3 also with a multiplicity of 2. That's 5 solutions, which is the maximum we can expect. We can expect 4 turning points because the highest power is 5. And our final problem here, now this might have been a little difficult. We have factored these before. You have to do it by grouping. You get x squared minus 25 times x minus 4, which further factors into x plus 5 times x minus 5 times x minus 4. And that gives us 5, negative 5, and 4, each with a multiplicity of 1. Since it is cubic, it can have at most 2 turning points. Now find a polynomial of degree n that has given zeros. There are a lot of solutions to this. Basically what you're going to do is you're going to set this up as factors. So let me give you a hint. You're going to do x minus negative 5 times x minus 0 times x minus 1 for the first one. Pause the recording, give it a try, and resume your recording to check your answer. And like I said, you just want to set those up as factors and multiply them out. You get x cubed plus 4x squared minus 5x. Now the next one's a little tricky because they only give you 2 zeros. So we know x minus 0 has to be 1 and x minus negative 4. However, we're supposed to have a degree of 5. That means you need to raise one of those 2 factors to the 4th power to get those extra factors in there. The easiest one to raise would be x to the 0. So x to the 4th times x plus 4 will work. There's some other solutions there, but personally I'd go with the first one, which is the easiest. And incidentally, you could multiply any of these solutions by a constant and get yet another answer that also satisfies the problem. Okay, now you're going to graph this function and then calculate the zeros and determine the multiplicity. Pause the recording, give it a try, and resume to check your answer. Okay, graphing it, we see we have 3 zeros. We have -1 with a multiplicity of 2. We have 3 with a multiplicity of 1, and 9 halves with a multiplicity of 1. The standard form of a polynomial equation is when you have the polynomial in descending order of exponents from left to right. To sketch a graph, you're going to examine the leading coefficient. You're going to factor and solve for zeros, plot some points, and sketch the graph. We also have something called the intermediate value theorem. It says that if a and b are real numbers and a is less than b, if f is a polynomial function and f of a and f of b are not equal, then in the interval from a to b, f will take on every value between f of a and f of b. Now what that means is, since polynomials are continuous and they don't have any breaks in them, if f of 1 is -8 and f of 4 is 5, then every value between -8 and 5 will be hit by the graph as it goes from where x equals 1 to x equals 4. It has to. You can't lift your pencil, so in order to get from -8 to 5, you're going to hit every value in between. Think of it like accelerating a car. If you go from 30 to 70, your car is going to go every speed from 30 to 70, even if it's for a split second. The theorem can be used to calculate zeros. So if you look at x cubed plus x squared plus 1, f of -2 gives you -3, f of -1 gives you +1. That tells me that somewhere in between -2 and -1, the graph has crossed the x-axis and there is a 0. So that can help you kind of figure out where it is. You can use a table of increments of 1/10 between -2 and -1, and you can narrow it down to between -1.5 and -1.4. You can continue narrowing it down from there and get it even more precise. And you just keep narrowing it down until you reach however accurate you need. Okay, here we have an example of a word problem. It says you plan to construct an open box from a square piece of material. It's 36 inches on one side by cutting equal squares with side lengths x from the corners and turning up the sides. And you can see the diagram there where it's illustrated how you're starting with that flat square and then you're going to cut these corners, turn up the sides, and then you'll have that little box. Write a function v that represents the volume of the box, determine the domain, use a graphing utility to construct a table that shows the height of the box with the corresponding volume, and use it to estimate the dimensions that will produce a maximum volume, and then use your graphing utility to graph the volume and estimate the value for x for which v of x is a maximum and compare that with what you got in C. So why don't you pause the recording and give this a try and then resume the recording to see how you did. So the volume is length times width times height, and the height is going to be determined by the squares that you cut out, which is x. So the height is x. The length and the width are the same since it's a square. It started out as 36 inches, but you're cutting out x on each side. So the box will have a length and width of 36 minus 2x. That means our volume is 36 minus 2x times 36 minus 2x times x. Or to put it in a little bit smaller form, x times 36 minus 2x squared. Notice we're not multiplying this out. We're just going to use it like that, which is great. The domain is from 0 to 18. The reason for that is that you have to cut something out, so you don't want x to be 0. Otherwise, you can't make the box. And if you cut out 18 inches, well, you're cutting 18 from both ends of the same side, and the side's only 36 inches long, so you'd be cutting off the entire side. So your domain must be from 0 to 18, and because the length and the width must both be positive. Okay, so for part C, we have to look over to the right here. And we've got a table with heights from 1 through 7. with the width and the volume, and you can look at that and see that the values go up until we get to, let's see, about 6 inches. That's the highest from this chart, and then after 6 inches the volume starts to go back down. So you didn't have to make try every number in the domain just until you saw the progression start to diminish. So according to our table, the maximum volume is going to be 3,456 cubic inches. The height will be 6 inches, and the length and the width will each be 24 inches. And then for part D, go back over to the left, and you see the graph. And the maximum point on the graph does occur at x equals 6, and this agrees with what we found in part C. Okay, here's another practical example. We have the revenues in millions of dollars for a company from 2003 through 2010. It's modeled by this 4th degree polynomial where t is between 3 and 10. By the way, revenue is the money that a company will bring in. Cost is how much they spend, revenue is what they bring in, and profit is the difference between the two. So you're going to use a graphing utility to approximate any relative extremis, so maxes and mins, over the domain from 3 to 10. You're going to approximate the intervals for which it's increasing and decreasing, and then use the results to describe the revenue. Pause the recording, give this a try, and resume to check your answer. So here's our graph. We have the relative maxima at 4.11, 21.87, and at 9.02, 29.25, and then the minimum 6.01, 18.81. It's increasing from x equals 3 to x equals 4.11, and from x equals 6.01 to x equals 9.02. It's decreasing from 4.11 to 6.01, and from x equals 9.02 to 10. Now, describing it is going to have some differences. Here's a possibility. The company increased in revenue from 2003 until January 2004, and then again from January 2006 until January 2009. Remember, your values for X are time, so these represent the years. The revenue decreased from January 2004 to January 2006, and then again from January 2009 to 2010. So that's a possible description of what you're seeing.